Okay, what I want to do now is talk a little bit about some other ways in which we can calculate the change in internal energy and enthalpy of a substance. Okay, this is kind of good and bad, I think. It's good because we need it, and it's good because it's very helpful for us, but it's bad when you start learning multiple ways of doing things, because I find students like it if there's just one way and they just repeat it every single time. And then when I start saying, oh, well, there's actually different ways to do the same thing, I think students start going, ah, man, why do you have to tell me two different ways of doing the same thing? You know, I like just one way. Keep it simple. Now you got to tell me there's two ways to do the same thing that there was before with just one way. Yes, there is, and we need to know both ways, okay? So I decided to come up with this kind of example here to help us think through the whole process of how we change between different states of a substance, okay? Solid, liquid, vapor, how we change between those states, okay? And we're going to deal with water. Everybody knows ice. Everybody knows water, okay? So I think this will be a good example we can all relate to, okay? But also introduce some new concepts as we walk through this a little bit, okay? That are going to be critical to this class, okay? Really important concepts. And of course, this is not the only time we'll cover it, but at least we want to talk about it. Okay, so what we're going to think about is I want you to imagine a block of ice. Okay, it's not a very big block of ice because it's only a kilogram, but you know, you get the idea. A kilogram of ice, decent little size of block ice. Okay, and I want you to imagine that ice really, really cold, okay? Minus 40 degrees C. Okay, so this is well below freezing. This is really, really cold ice. This is the kind of ice that you might get. You go over to Zero Mountain and you go over there to their cold storage facility. You go, okay, I want some really cold ice. I don't want to just have ice that's just ready to melt. I want it cold, cold, cold. So I decided to choose minus 40 degrees C because I always like that because, you know, minus 40 degrees C and minus 40 degrees Fahrenheit are the same temperature. It's always an interesting little trivia question there. But it's minus 40 degrees Celsius. So it's really, really cold ice. Okay, same as minus 40 degrees Fahrenheit. Okay, same temperature. And we want to ask ourselves here, what amount of heat does it take to take that really, really cold ice, okay, and turn it into ice that's just about to melt, okay? But remember, we're not talking about a phase change in this process, okay? It's still solid ice in both before and after, okay? So I got 1 kilogram of ice at minus 40 degrees C, and then I'm going to turn it into ice that's just about to melt. Well, obviously, if it's just about to melt, it's going to be basically at 0 degrees C, but it hasn't melted yet. It's just gotten to that point. So the real question that we're talking about here is how do we calculate the amount of heat transfer, or really, I ought to say, maybe a note below it, say, how do we calculate the change in internal energy okay? Not just the amount of heat transfer, but both cases are fine, okay? When dealing with solids, okay, solids, what do we do when we have solids? Okay, I'm not talking about gases, I'm not talking about liquids, I'm talking about solids, and that's going to be really important, okay? It's going to be really important. So we're talking about just solids, no phase changes here, just solids, solids that change temperature, okay? How do we do that? Well, we have a concept that's going to be really important for us a lot of times in class, and you've probably heard it already. It's called the specific heat, okay? Specific heat. The specific heat is denoted by the letter C. Okay, specific heat has a little c. Okay? You look it up in the back of the book. You look it up for various substances. Okay? You look it up. By the way, let me take you to that table. It's one of the first tables you're going to get. It's down here. For solids, it is table A3, but you're going to have to scroll to the next page or whatever. Table A3, properties of common liquid, solids, and food. And solids are given right here, okay? So lots of solids. What I want you to look at right now, ice, since we're talking about ice, you'll notice that they gave me a bunch of specific heats. They didn't just give me one. Because technically the specific heat of ice does vary with the temperature of the ice, okay? Now, ice that's just about to melt, that would be 273 Kelvin, right? That ice has a specific heat of 2.11, and the units are given on the top, kilojoules per kilogram K. But if ice is colder, let's say it's 40 degrees below Celsius, then it's pretty close to 240 K, kind of, right? So it would probably be around 1.86. So the specific heat of ice varies with temperature. In fact, the specific heat of a lot of different things varies with temperature. And sometimes we need to take that into account. But honestly, most of the time what we do is we just pick one in the middle. So if we have a temperature range like we do here from minus 40 degrees to 0, why don't you just pick one in the middle? Okay, just pick at minus 20. So what I decided to do was, if you look at 260K, 260K is 13 below Celsius. That's about 2. I just went with 2. Okay, I'm going to go with 2 for the specific heat of ice. Okay, so I'm going to say the specific heat of ice in the temperature range we care about is about 2 kilojoules per kilogram K. All right. How does that help us? Here's how that helps us. If I want to calculate, and this makes life a lot easier for us, if I want to calculate the change in internal energy of a solid, it is equal to the specific heat of the solid times T2 minus T1. That's easy. That's really easy. All you have to do is get the specific heat of the solid and multiply by the temperature difference, and bang, you got this change in internal energy. So let's do this as an example. The change in internal energy, and I'm going to do big U because remember I said 1 kilogram. So the change in internal energy is equal to C times T2 minus T1 multiplied by the mass. The mass is just 1 kilogram here. Okay? So let me fill in the numbers here. Okay? This is going to be 2 kilojoules per kilogram K times T2, which is 0 minus a negative 40 times 1 kilogram. Yeah, this is good. I just reading my mind. Very good question. They say, well, hold on a second. Those units are in Kelvin. It says kilojoules per kilogram Kelvin, but yet I just put down stuff that's in Celsius. But here's the deal, though. If I have a temperature difference in Celsius, it's the same as a temperature difference in Kelvin. So it does not matter in this case. If I were to convert both of these two temperatures in Celsius to Kelvin, you would still have the same temperature difference. So it doesn't change anything. So you can be loose like this and just go ahead and throw it in. It will work out. Okay. So you calculate this number. It's pretty simple. You get the change in internal energy is 80 kilojoules. Okay. By the way, I said, how do we calculate the amount of heat transfer? That's actually really simple. It's the same value, because if you go to the first law of thermodynamics, I don't have a lot of space here, but let me do it up here. If you go to the first law of thermodynamics, remember the first law says Q minus W equals change in U plus change in kinetic energy plus change in potential energy. Well, there's no work here. There's no work, there's no kinetic, there's no potential. So in this case, in all the cases that we have in my example, Q is equal to change in U. So what's the Q? It's the same as the change in internal energy. Basically, it says, how much heat do I have to transfer into that ice to warm it up from minus 40 degrees Celsius to where it's just ready to melt? The amount of heat for 1 kilogram of ice is going to be 80 kilojoules, because it's going to be its change in internal energy. That's going to be the heat transfer. Okay? That's pretty easy, right? Honestly, you're going to love specific heats once you get used to them, because it makes life so easy. It really does. Specific heats. If you want to get a change in internal energy or a change in enthalpy, which I'll talk about here with gases, it's easy. Okay, it's nice. Everybody likes specific heats, but the problem is it gets frustrating because you now have learned a different way of doing things. Now, when it comes to, though, solids and liquids, there is no different way. You have no other way to get the change in internal energy of a solid than to use specific heats. You get that? There's no other way. There's no other way with liquids, too. Okay? It's only gases that you have these multiple options. Okay. All right. The next part here. Ice that's just about to melt, turning into water. Okay, so how do we calculate the amount of heat transfer, or, like I said, change in internal energy? Same thing. How do we calculate that? Now, this is ice that's just about to melt to water. Now we have a phase change. Notice we don't have a temperature change. We don't have a temperature change, but we have a phase change. Okay. There's a term for this to calculate this amount of change in internal energy. It's called the latent heat of fusion. And again, you look it up. It's called the latent heat of fusion. It's basically the amount of energy to melt the ice. It's the amount of energy to turn a solid into a liquid. It obviously varies with what you're talking about. What solid are we talking about? If this is ice, you could probably imagine it doesn't take a lot of energy to turn ice into water. If this is steel, it probably takes a whole lot of energy to turn steel into liquid steel. Yeah, it does. So it's a lot different depending on the substance, right? Okay, so it turns out that the latent heat of fusion for water, for ice to water, you look this up, is 333.7 kilojoules per kilogram. Okay? Therefore, it's that simple. The change in internal energy is equal to 337 kilojoules, right? Because it's just 1 kilogram. Again, you just look this up. You look it up. It's called the latent heat of fusion, because we have a phase change here. You're not changing its temperature. You're just changing its phase from ice to water. 337 kilojoules is what it takes. Oops, 333. Sorry, I should. 333.7. Yeah, which is just 1. Mass 1. Yeah. There. Yeah, multiplied it by mass of 1 kilogram, so yeah, same thing. Okay? So as you can tell, it takes more energy to melt the ice than it does to change it from minus 40 to 0. Didn't take very much energy to warm it up, but to melt it, it took more energy. And it took quite a bit more energy to melt it. All right, now, Now it's all liquid. Now we got all liquid. We got liquid water at 0 degrees Celsius. It just all melted. And now we want to heat it up to 100 degrees Celsius. That's the next thing. Now we're not doing a phase change here. This is all liquid water. So the question is, how do we calculate the amount of heat transfer, or how do we calculate the change in internal energy? Really the same thing. When dealing with liquids, what do we do? What do we do with liquids? Well, it's the same thing that we do with solids, that we do with liquids. We apply specific heat. Okay? So again, with liquids and solids, you have no other choice. You have to use specific heats. That's why specific heats are so important. Specific heats. Okay? So we got to look up the specific heat of water. Okay? We're going to go back to your tables here and say, well, what's the specific heat of water? What's the specific heat of water? Well, let's go back to our tables. Okay? Specific heat of common liquid, solids, and foods, table A3, liquids. You got a bunch of liquids there. Okay? The last column there is the specific heat of water. Right? It's the last column, specific heats, and the bottom there is water. Okay? Notice the specific heat of water does change as you go from 0 to 100 degrees Celsius. And by the way, this is assuming standard pressure. I went with 4.2. And again, it's the same units. So I'm going to say specific heat of water, 4.2 kilojoules per kilogram K. So again, it's pretty easy to calculate the change in internal energy. The change in internal energy is equal to the specific heat times T2 minus T1 times the mass. Specific heat is 4.2 kilojoules per kilogram K. The change in temperature is 100 minus 0, right? And the mass again is 1 kilogram. So the math is very simple. This is going to be 420 kilojoules. Okay? Whenever we're dealing with liquids and solids, there is no other way. We have to use specific heats. There is no other way to get the change in internal energy. So anytime you see a problem, and we're going to see some starting next week and the next few weeks, and the problems will involve liquids and solids, specific heat, specific heat, specific heat. You need to use it. There's almost no way to escape it. You're going to use it at some point whenever you see liquids and solids. Okay? And we're going to use it a lot with water as we go on the semester, because water is used a lot in power plant operations. You know, there's a reason why we put power plants a lot of times near water. It's cooling, helps cool. Okay? Well, a lot of times that cooling water, how do we calculate the change in internal energy of it? Specific heats. So it'll come up a lot. Okay. All right, so next page here. Now, water at 100 degrees Celsius to steam at 100 degrees Celsius. Okay? So now we're going to boil off all the water. Okay? Again, this is a phase change. Okay, this is a phase change. So how do we calculate the internal energy? Whenever you have a phase change, you've got to take that into account. There is a term for this. It's called the latent heat of vaporization okay? The latent heat of vaporization, okay? And the change in internal energy then would be equal to the latent heat of vaporization times the mass. Okay, I don't know. Latent heat. Let's just do it like that. You just look that up in the table times the mass, okay? Which for water, standard pressure is 2257 kilojoules per kilogram. Multiply that by 1 kilogram of water, and we're going to get 2257 kilojoules. That's the change in internal energy.
Do we have to memorize all those for tests and stuff like that?
No. You have your tables. Yeah, tables. So.
But we have to know
Okay.
the different latent heat and vaporization and fusion for different phase changes.
Yeah, you'd have to know that the latent heat of vaporization corresponds to boiling off something, or the latent heat of fusion corresponds to melting something. Yeah, you would have to know that. Yeah. Okay. Now let me make sure I check one thing though. I think, and I want to make sure of this. The latent heat of vaporization here. I think I may have something I need to correct on that. Yeah. It's actually the change. That's what I thought. This is actually a change in H. Okay, because generally it's pretty hard. In most cases, it's normally when you boil something off and you vaporize it, it's in a controlled volume. It's in an open situation. It's flow. So they call it change in H. Okay. By the way, I said there's two ways to calculate it. That's one. You can use the latent heat of vaporization. And the other way, of course, is just use tables. Because if you take a look at your tables for saturated water, and you look at 100 degrees Celsius, and you look at the evap term, if you look at the evap term for H, it'd be HFG. It's equal to 2257 kilojoules per kilogram. So you get the same answer. It's the same thing. It literally is the same thing. Latent heat of vaporization is basically how much heat do you have to do to take it from water, liquid, to steam, to a gas, to a vapor. Well, it's that amount of heat, and that amount of energy change. So it's the same thing. Okay, lastly, so this by the way is our largest change. Big change there. Lastly, so it takes a lot of energy to boil off water. Lastly, steam at 100 degrees Celsius to steam at 250 degrees Celsius. Now we're heating it up even more, okay? All right? So we're heating it up even more. Can you apply specific heats for gases? Yes. The answer is yes. Yes. So specific heats can also be applied to gases. But we have to make it a little bit more complicated, don't we? We do, because with gases comes the possibility of compressibility. Gases can compress, they can expand, where liquids and solids don't do that so easily. And so we have actually two different types of specific heats for gases, okay? We have a C sub V, okay, which is the specific heat at a constant volume, and that is going to be equal to the change in, well, let me do it this way. Let me change it up. We can calculate the change in internal energy by applying the specific heat times T2 minus T1. And that's specific heat C sub V, okay? So V stands for constant volume. But we can also calculate the change in enthalpy. That would be like for an open system, right? For a control volume. That's going to be equal to C sub P times T2 minus T1. Yeah, unfortunately, we got to make it more complicated. This stands for constant pressure. Okay? If we have a truly closed system that has steam and we want to know what its change in internal energy is, you can use C sub V. If it's in a flow situation, like most cases will be, you're going to use C sub P. So you're going to use C sub P more than C sub V, but you're going to use them both. Okay? And so that's how you can do that in this case. By the way, for steam, let me show you this here. For steam, C sub P. I think it's earlier. Here we go. That's oxygen. Here we go. It's on table A2, ideal gas, specific heats at various common gases. This one says at 300 K, so it's not, may not be exactly where you're at, but, there's lots of tables. But here's you got C sub P and C sub V here. C sub P is always going to be greater than C sub V. But you have to have them both, unfortunately, for gases. Okay. But steam, by the way, is at 1.8723. So you can use the change in H of steam as 1.8723 times T2 minus T1, which in this case would be 250 minus 100. Okay. You can calculate that. But you can also just look it up in the tables, right? You can also just use tables. Okay, you can use tables. And in this case, you could find the H2 as equal to 2974.5. Oops. And H1 is equal to 2675.0. And you'll find that in both cases, the change in H is about the same. They're pretty close, whether you use specific heats or whether you use tables. But let me tell you this. If you have tables, use tables. Okay? If you have tables, use tables. That's why we won't use specific heats a ton for gases, because most of the gases we use are either steam or air, and we do have tabular data for air even too, which I'll show you later on. Okay? We do have some tabular data, but sometimes we'll use it for air. We will use it sometimes for air. Okay? We probably won't use it much for steam because we got tables for steam. Okay? All right, we got a few minutes here.